You see, if you're going to say trigonometry is what you want to look at, the thing is, depending on what we're going to do, we're likely to touch and talk about things that you already know. Because when I think of trigonometry, trigonometry, obviously in grade 10, the one thing that's introduced when you hear trigonometry is sine, cos, and tan. So sine, cos, and tan is what we refer to as functions. So when I say functions, I just mean the idea that when you think of sine, right, there'll always be something to put inside here. When you think of cos, there'll always be something to put in here. When you think of tan, there'll always be something to put in there. Now, what we already know is if you put the same value in each of these, you will obviously be getting different outcomes. The reason why you'll be getting different outcomes is because each of these individual expressions, sine, cos, and tan, they produce something specific. You see. Now, in grade 10, right, the basics of trigonometry is introduced when we will be working with a right angled triangle. So let me put here right angled triangle. So when you think of a right angled triangle, right, you want to think of a triangle that has a 90-degree angle. Whether it's pointing to the right or the left, that doesn't matter. The idea of right angled refers to a triangle having a 90-degree angle. So I'll deliberately even make this triangle look something like this. See, because someone once asked if a right angled triangle means it's facing to the right. That's not it. A right angled triangle is a triangle that has a 90-degree angle somewhere. This can be any angle, and this can be any other one, but this has to be 90. Now we know that all interior angles of a triangle add up to 180. So whatever these two are, they also add up to 90. So with this right angled triangle, the idea is depending on which angle you are standing at. So let's put x over here. So if you put x over here, let's do this. Let's put x over here. If you put x over here, right, you have to remember that if x is here, this here is the opposite in relation to where x is. And then this here is the adjacent in relation to where x is. Now, the angle that is always opposite the 90 degree, we always refer to that as the hypotenuse. You see, that's the line opposite the 90-degree angle. So the line opposite the 90-degree angle, regardless of how the alignment of your triangle is, the angle, the line opposite the 90-degree angle, that's the line that will always be the hypotenuse. So with us knowing that, the one idea is if you have an angle here, let's label this angle X, Y. The angle Y here, if Y is here, you have to remember that depending on where Y is, it's only the hypotenuse that stays the hypotenuse, because the hypotenuse is always the line that is opposite the 90-degree angle. But then if you're dealing with Y, this one here is the one that becomes the opposite. Because if Y is here, this line is the one that's at the opposite. And then if Y is here, it means that this line is the one that's at the adjacent. You see. So that's what we should like keep in mind. This is the one at the, this is the line at the adjacent. This is the line that's opposite. This is the line that's the hypotenuse. Now, where you put the adjacent and the opposite, it's all dependent on which angle you're dealing with. You see. So that's the big idea. So when we're dealing with, let's say, x, as we have been talking about, if x is here, right, what we already know is that sine x, these three will always be equal to a specific fraction. And we know a fraction is a ratio. So that's why they'll refer to it also as a ratio. So we know the ratio for sine is opposite over hypotenuse. So that's like opposite over hypotenuse. The ratio for cos is adjacent over hypotenuse. So you have a over h there. And then last but not least, you have tan. The ratio for tan is opposite over adjacent. So this is opposite over adjacent. You see. So that's the big idea, opposite over adjacent. So these three here, remembering these three ratios, normally you can actually just think of some kind of an acronym that you can always use. No, not an acronym, a phrase that you can use to remember these three. And the phrase I usually use is, oh heavens, another hour of algebra. That's what allows you to at least be able to remember the O over H, the A over H, and the O over H. It's oh heavens, another hour of algebra. You see, sometimes people may say something like Sokatoa, so ka toa. So this is to remember that with sine, it's opposite over hypotenuse. With cos, it's adjacent over hypotenuse. With tan, it's opposite over hypotenuse. That's the big idea with these three here. You see, so ka toa, like that. Now, the big idea is that once you know all this is more like the basics of trigonometry, like where it really starts. Now, with this being said, what we do need to recognize is that with trigonometry, right, there is then other different formulas for different things that we need to know. One of the formulas we need to know is that sine x, or rather, let me write 10x. One of the things we need to know is that 10x is the same as sine x over cos x. This is more like a law, you see. So what that means is, regardless of what x is, x can be a specific angle, x can be two values put together, it doesn't matter. Whatever this value is, it's the value that goes up there, it's the value that goes down there. So when you're seeing something like orange, right, like 10 a plus b, this can be written as sine with the a plus b on top, and then the cos a plus b at the bottom, you see. So this is what we can keep in mind. The fact that regardless of what this is, it will always be this part also, and it will always be this part as well. Now, there's also then one, this here is just like the tree. This is just for 10. It's just an identity for 10 to say that 10x is equal to this thing here. So when it's flipped over, right, if you have, let's say, 1 over 10x, then it means this is flipped over also. You have cos x at the top, sine x at the bottom. Because remember, with 10x, right, this is something over 1. You see, this is something on top of 1. So because this is something on top of 1, if you flip it over, right, like this, the 1 goes on top, the 10x goes at the bottom. As long as you do that, it means that these also get flipped over. The sine goes at the bottom, the cos goes on the top. So these are almost ways of saying that with trigonometry. Trigonometry comes with, different kinds of formulas that a person needs to remember when they are going to be doing whatever it is that they're going to be doing. Because if you don't remember these tiny formulas, yeah, it's gonna be a problem. But the only way to really then remember these formulas is to bit by bit just be using them. One of the ones that I can mention, right, is what we refer to as the square identity. Let me put here square identity. And maybe put it in blue. This nice blue here. Square identity. The square identity looks as follows. Basically says sine squared an angle plus cos squared an angle. This is always equal to 1. This is what the square identity says. So the square identity says the value here plus the value there. If you're squaring both of them individually, it will always be equal to 1. Now the thing is, because this is an equation, it also then means if this cos goes to the other side, you also are left with something that says sine squared x, right? If the cos goes to the other side, you'll have 1 minus cos squared x. And then with the cos, if the cos remains and the sine is the one that goes over, here's what you're going to have. The cos remains, right? And you're going to have 1 minus sine squared x. So this is all coming from the main thing here. The main thing which says sine squared x plus cos squared x is equal to 1. You see. So this is some of like the basics of trigonometry that you would need to know before we dive into other aspects of trigonometry, which is things like the graphs that each of these functions draw. Okay. Because when we're thinking of trigonometry, it's such a broad topic because there are cases like now, right, where you're dealing with triangles. If you were just dealing with triangles. And then when we think of the square identity, here we'll be dealing with cases where you would be needing to like break down stuff and all that. You know, in addition to this kind of work where you need to like break down stuff, I mean, in addition to this, you can also talk about trig graphs. This is trig graphs. Now, the idea behind trig graphs is the fact that if we have what we have here, right? If we have a sine graph, the equation would be y is equal to sine x. Now, the idea is if y is equal to sine x, it basically means that this is a function. It's a graph, and you can actually draw it out. Now, any trig graph has two things in particular for grade 10 that you need to look out for. Now, with the cos, sine, and the tan graph, let's do a sine one first. Sine graph, it's in the format a sine bx. Now, the thing is, a stands for something. A stands for amplitude. Amplitude. And then B stands for frequency. Now, all these two here both have a formula. When C and then Y. This is the amplitude, this is the frequency. So what we know is that A being the amplitude, B being the frequency. What we need to keep in mind is the fact that the formulas for each of these are as follows. For A looks like this. The maximum Y value minus the minimum X value. No. The maximum Y value minus the minimum Y value. And then you divide by 2. This will always give you the amplitude. And then for frequency also has a formula. And that formula introduces something else of our graph. So B, which is the frequency, right? Let me just actually write it like this. Frequency is equal to 360 divided by the period. This is referring to a cost graph, like the actual graph that you will be drawing out on like a piece of, on like some Cartesian plane kind of format. So you have what you refer to as the frequency, you have what you refer to as the period. And the 360 is a fixed number in the formula. Now remember, this is specifically for a sine graph. A is the amplitude, B is the frequency. Now the idea is, with a standard graph like this, you see this standard equation. This standard equation has two particular pieces of information. And that piece of information is, for example, the first one here is a 1. Second one here, also a 1. Because the number on the far left of sine is a 1. The number directly next to x is also a 1. Okay. So this is telling you the frequency is a 1, the amplitude is a 1. So the question may be, what is frequency? Frequency is basically the number of graphs that you will see in a space of 360. So let me write it as a definition. Frequency, the number of complete graphs, the number of complete graphs, the number of complete graphs in a space of 360 degrees. You see, so when I say 360 degrees, this is specifically only for a sine and a cos graph. Then one point square bracket. So let me put round bracket. This only specifically applies to square brackets and no, this only applies to a sine graph and a cos graph. That's 360 part. For a 10 graph, it would be 180. But the idea is that's what frequency is. Frequency is the number of complete graphs in a space of 360. Now the period also has this same formula, but the frequency will just be swapped around. Like if you want to work out the period instead, you just write a formula like this. Period is equal to 360 divided by the frequency. See, that's what you need to keep in mind. The period is the first thing. If you need to work out the period, you just take the 360, you divide it by the frequency. If you need to work out the frequency, you just take the 360 and you divide it by the period. Now the idea is the period now also has its own definition, which is also like simple to remember. The period is the number of degrees it takes to get a complete graph. So here period is the number of degrees it takes. Let me put this thing a bit bigger. The number of degrees it takes, right, to get a complete graph. That's what the period is. The period is the number of degrees it takes to get a complete graph. So with that being said, right, when we will draw this picture, a standard sine graph, if you can remember, it looks something like this. From 0 to 360, you have, it goes up to like 1, it goes down like -1, you see, and then it goes back up to 360. I mean, it goes down to somewhere at 180, right? It will be down here at -1. Somewhere here, it will be at 270. Somewhere here, it will be at 90. No, this is a cos graph. Dang it. I'm busy drawing a cos graph here. But a sine graph goes up, down, and then up, down, and then up again. So here it's going to go up like 90, comes down at 180, and then at 270 it's going to be down here at -1, and then from 270 it's going to go back up to 360. This is a sine graph, a standard sine graph. Goes up to +1, goes down to -1. Now with this graph here, you can see in a space of 360, we have one graph, which is what our definition is going to supplement to say we have one frequency. I mean, the frequencies are one. It's the number of complete graphs in a space of 360. In a space of 360, the reason why we're saying we have one complete graph is because if you were to keep going the way we have just laid this out, if this thing was to like extend going onwards, and if this was also to extend going backwards, what you would have is a situation where you see from here, a new sine graph would begin, you see. And then from here, going backwards, this is where another sine graph was like ended. Because a full graph is always from one specific point where the same motion is about to repeat. So you see here, this motion of you going upwards like this, it would start to repeat somewhere there. That's how you know that from here to there, that's a full graph. Now to make life a bit easier, even if you had, let's say, a graph that looks like this, right? But then this is 0, this is 40, this is 90 in the middle here, this would then be 180. If you have a situation like this, the period of this graph is 180, because in a space of 180 degrees, you have one full graph. But then in a space of 360 degrees, just because of how this graph is behaving, you would have had two full graphs in a space of 360. So the period here is still 180, but then the frequency is a 2. You see, the frequency is a 2 because in a space of 360, you have two full graphs. The frequency, the period is 180 because it takes 180 degrees for you to have one full graph. So in this image, the period is 360, but then the frequencies are 1. Just write this a bit better. 360, 360, and then the frequencies are 1. Frequency is a 1. There you go. Because in a space of 360, you have one graph, but in that space of 360, you have, but it's taking 360 to get a full graph. So period is 360, frequency is 1. Here, period is 180 because it takes 180 degrees to get a full graph, and then in a space of 360, you have two full graphs. And what we can see is a full graph is happening every 180 degrees, you see, because what we already know is that one way or the other, this position here, okay, this is in the middle of 180 and 360. So 180 plus 360 divided by 2, this is giving us 270, right, in the middle here. You see. Now the big idea is it doesn't matter where you want to look from and where you want to end up. A full graph will always be from one place where the same motion is starting to another portion where that same motion is ending. So here, even if you look from here, from this 90 to 270, this is a full graph. The reason why you consider this a full graph is because it's starting off by going down here, and then here it was about to go down again. So that would be a full graph. From here to from 90 to 270, if you look nicely, it's still a space of 180 degrees. So the point I'm trying to make is that it doesn't matter which point you start with. You will have a full graph when that same motion is about to repeat itself. So as long as, so you see here you're starting by going downwards, right? Down, up, and then here you are. The moment you're about to go down again like that, that's when this is about to restart. So that's why, this today is a full graph. That's for a sine graph. Now the same applies for even a cos graph. And with the tan graph, it's just different. Because with the tan graph, its normal standard period is 180. So with these formulas for a tan graph, the number here is 180 and the number there is 180. But let's do one with a tan graph for now, because with the cos graph, it's more or less the same as the sine. But we'll do tan first, and then we'll actually go to sine as a way to almost recap on the stuff we said about a sine graph when we'll be talking about a cos one. So with a tan graph, the tan graph. A tan graph, fortunately, is it is what it is. A tan graph is a special looking graph. It looks as follows. I'll draw it first, and then we'll just explain what the different pieces of information will be telling us. So what we already know about a tan graph is that it has asymptotes. Somewhere at 90 here, it is an asymptote. Somewhere at 270, there's an asymptote. Now, the reason why I'm drawing it like this, there's an asymptote over here, and then there's an asymptote over there, which is a line that the graph does not touch. Now, the big idea is a full graph is actually in a space of 180, like a standard one. So you'll have a curve that looks something like this. It passes 180 here. Then you have a curve that points down like that. This is what you consider a full tan graph. You see, from 90 to 270, that's 180 degrees. Now, this curve basically repeats every single time in between your asymptotes. So you see, asymptotes basically span a space of 180 degrees. So in our case, this is where your other asymptote would be on the far left here. because from 90 to negative 90, that's a space of 180 degrees, you see. So this space of 180 degrees, what we already know is that this goes up like that, and this would then go down like that, you see. And then from 270, right, another 180 degrees. From 270 going onwards, 180 degrees later would be somewhere at 450. Somewhere here you'd have 450. Now, in between that 270 and the 450, you'll have a full 10 graph. You see, it looks like this, looks like this. There we go. You see. So that's what a 10 graph looks like. But the thing is, remember, we are used to seeing it from 0 to 360. See, so us being used to seeing it from 0 to 360, what we normally see is this curve popping up, and then this squiggly line in the middle, and then this curve at the end. That's what we normally see. But the point I'm trying to make is it doesn't matter. What you should be able to recognize is the fact that a standard 10 graph, the equation of this graph would look something like y is equal to 10x. Now, the number in front of x is still referred to as the frequency. So if you were to put a standard form for this equation, you'd say y is equal to, let's use a different variable here, k, and then 10 bx. The reason I'm still using bx for this part here is because b will always be the frequency for any graph. But then the thing is, with the 10 graph, it does not necessarily have an amplitude. So that's why I would not want to write the letter in front here as a, because it might confuse it with a for amplitude. But a 10 graph does not have amplitude. K is more like the stretch. The higher the k value, the more stretched out this curve will be. It'll be at a point where it almost seems straight. You know, if k is a very, very high number. So if k is a high number, it's this line here is basically less squiggly. You know, it's more like maybe a bit too narrowish. So in this situation, what we know about b is that b is the frequency. Now we already said with the 10 graph, you use 180 instead of using 360. So with a graph like this one, the frequency is 180 divided by the period. Period. And then the other way around. If you want the period, you're gonna say 180 divided by the frequency. You see, that's how this works. If you want period, frequency goes down there. If you want frequency, period is the one that goes down there. Now, with what we have just drawn out, we can easily tell what the frequency is and what the period is. In this graph, the frequencies are 1 because in a space of 180 degrees, you have one graph. The period is 180 degrees because it's taking 180 degrees to get a full graph. You see. From here to there, that's full graph, 180 degrees in total. From here to there, another 180. From here to there, another 180. You see. That's why here we can see the frequency is 1, but then the period is equal to 180 degrees, because in a space of 180 degrees, that's where you're getting a full graph. You see. So all this being said, you need to keep in mind that with a cos graph, everything we mentioned about this sine graph still applies. Amplitude is the same, frequency, you work it out the same. The only thing with the cos graph is we can maybe just draw the image. But before drawing the image of the cos graph, what we can just maybe illustrate is what would happen if the frequency of this 10 graph becomes a 2. If the frequency of our 10 graph was a 2, basically means that that the time it takes for you to get a full graph will be less. Okay. So what I mean is, instead of having an amplitude at 90, you would have an amplitude at 45. Instead of having the other one at 270, you would have it at 135. Remember, everything is now half. So your curve would still look like this. It would still do something like that. But as long as the frequency is a 2, in this situation, for this pink portion, our graph, the frequency would be equal to 2. Huh? 2. Really? Yeah, 2. The reason why the frequency would be equal to 2 is because in a space of 180 degrees, you would have 2 full graphs. So to illustrate that, you can see going onwards, right, from here to the next asymptote, that's like 90 degrees later. So from here, 90 degrees later, that is obviously going to be 225, 225, you see. So 225, that's like this point in the middle here. This goes upwards, this goes downwards. There you go. Now, this is what we need to keep in mind. You see, the frequency here would be at 2, but then the period would be 90 degrees. Because from 45 to 135, that's 90 degrees. From 135 to 225, that's also 90 degrees. And the equation of this graph would look something like y is equal to 10 to x. For the number directly next to x, that's your frequency. And as long as you have your frequency, you can work out the period, you see, because even if we had to use the formula is telling us that the frequency is equal to 180 divided by the period. So if you put the equation, if you put the numbers in the equation, the period is, if we're looking for the period rather, we said it's the other way around. We wrote on the formulas. I don't even know I'm rewriting them. But then if you wanted to use our formulas, right, to get the period and the frequency, the thing is, if you had to get the frequency looking at the image, you would just need to look how long it's taking to get a full graph. Because if you're going to look for frequency, you need the period. So you'd have looked for the period first, so you can put it in your formula to get the frequency. So looking at your graph, you would look, okay, from 45 to 135. It looks like it's a full graph over there. So if you're gonna get your frequency, you'd have 180 divided by the distance between 45 and 135. That's 90. You put your 90 here, and then this is 180 divided by 90. That's it, 2. And then here, 180 divided by frequency. I mean, like if for the second one, I mean, you already figured out the period. But then say you did not figure it out. You would then ask yourself, in a space of 180, how many full graphs do you see? You see full 10 graphs. So for the period, you'd have said 180. In a space of 180 degrees, you're seeing 2 full graphs. So you put a 2 here. 180 divided by 2, that would be your 90 over there. Is it? So that's the idea with the 10 graphs. And the last thing we can maybe just touch on in terms of these graphs is obviously a cost graph. Now, the idea with the cost graph is that it has quite a few similarities to a sine graph. Because with the cost graph, remember the equation could be y is equal to cos x. And based on the standard form would be like y is equal to a cos bx. So we already said a is the amplitude. We might as well even recap the formula. We said it's the maximum y value minus the minimum y value. The whole thing over 2. So with that being said, right, the whole thing over 2, that's amplitude, as we know. The other one is frequency. The frequency is going to be equal to 360 divided by the period. That's what frequency is. And what we know is that the period is also then just swapped over. 360 divided by the frequency. 360 divided by the frequency. There we go. So with that being said, right, what we need to then keep in mind is the fact that with a picture of a cost graph, we should not expect anything crazy, but we already know what it looks like, but we can just explain certain things that you always need to remember. So you always want to be able to draw out the basic image of these graphs. Because normally when you're able to draw the basic images of this graph, you you would be you would be allowing yourself to get acquainted to this kind of work very well. Because if you can draw the image, all that, yeah, you're putting yourself in a good spot. So with the coarse graph, we know that what we normally see is it's starting well with what I like to show is the bigger picture, because most of the time if you're only focusing on something like from 0 to 360, you tend to then miss the point. To say with trigonometry, these graphs just go on forever. They go all the way to the left, they go all the way to the right. So we should not like overcomplicate things. But anyways, so this is like 0. In the middle here, you have 180. In the end there you have 360. Okay. So down here you have -1. Here you'll have a 90. Here you'll have a 270. Up here you have +1. So the image, we know it comes down, it passes 90, curves back up like that, comes down like this, curves like that, you know, curves like that, you know, goodness, and then like that. So to the left, you have a similar image. You see, like this, does that, like this, and then it goes back up, like that. So this here is like -90, -180, -270, -360. So the reason I'm drawing out this image like this is because I'm trying to give you the idea that these graphs, they just repeat, just go on and on and on. So in a situation like this one, I mean, like the frequency of this graph is just 1. Because in a space of 360, whether you're looking to the left or you're looking to the right, in a space of 360, you're just seeing one graph. And it is taking you 360 to get a full graph. So that's why the period is 360. So in this situation, the frequency, you know, your just like nice, just like nice. Frequency, the frequency in C is equal to 1, because in a space of 360, you're seeing one graph. The period is 360 degrees. The period is going to be equal to 360 degrees, because in a space of 360 degrees, you're seeing it's taking 360 degrees to see one full graph. That's what you should remember. You see, that's what you should remember. So that's the key thing. That's the key element. And yeah, you should just keep that kind of thing in mind. So obviously with this one, when the frequency increases, it means you'll be seeing a full graph in a much shorter space. So when I say you'll be seeing a full graph in a much shorter space, let's even crank things up. If your frequency was a 3, it means that every 120 degrees you have a full graph. So somewhere here, this is like 120. Another 120 degrees, that's at like 240. And then another, what you call, 120 degrees, that would be at 360. You see. So if you have 3 graphs in a space of 360, they would look like this. You would have a full graph here, it ends. Another one starts, it ends. And then lastly, another one starts, and then it ends. So on the left side, you can imagine you would be seeing the same thing. You see, your graph would just be starting and ending in a space of 120 degrees, starting and ending in a space of 120 degrees, and then starting and ending again, going on and on and on and on and on. You see? So let me just keep going like this. this graph would just keep going on and on and on and on and on. So in this image that I just drew here, right, this is a situation where if let's say up here, let's say it's a 2, down here it's minus 2. The equation of this graph would look something like y is equal to 2 cos 3x. The amplitude is a 2 because 2 minus negative 2 is a 4. And 4 divided by 2 gives you amplitude of 2. So here, amplitude would have been the maximum y value, which is a 2, minus the minimum y value, which is a negative 2. The whole thing over 2. 2 plus 2 is a 4. 4 over 2 is a 2. There you go. So with all this being said, right, that's why this is a 2. And in a space of 360 degrees, you're seeing 3 full graphs. That's why the frequency is a 3. That if you wanted to see, if you wanted to work it out manually, you could have just said, okay, how long is it taking to see a full picture? It's taking 120 degrees. So in your formula, you'd have said frequency is equal to 360 divided by 120, which is the period. Because it's taking 120 degrees to see a full picture. So the frequency is a 3. If let's say for some odd reason you did not know what the period was, but you can see that in a space of 360 of 3 graphs, to say the frequency is a 3. To get the period, you would have then just said the period is equal to 360. You divide by the frequency, which you would be seeing is like 3 full graphs in a space of 360. And then you get your 120. This would give you your period. And that's how you work out these kinds of things. You see, that's how you work out these kinds of things. So that's for a sine graph, a cos graph, and a tan graph, and obviously the basics of trigonometry, which is SOHCAHTOA. The left-hand side, right-hand side, and then the hypotenuse. We say these are interchangeable depending on where you're looking from. Amplitude and frequency, you calculate it the same for sine and the cos graph, and then for a tan graph, instead of using 360, you would just be using 180 instead. So yeah, in terms of the basics for trigonometry, these are the basics that you somewhat at least need to know in the time being. I'll just stop this one here. Stop.